All right, so let's continue our discussions related to ESC201P here. And in the first lab, we had looked at use of circuit simulation as a tool to understand and design circuits. And so let's continue with that discussion and see how we can use circuit simulation. For example, in this particular lab, how we can use it to gain insight into circuits. All right, so let me open up. I hope all of you have installed the microcap simulator and become a little bit familiar. So in this particular lab also, we'll use that particular simulator, and that would help us become more familiar with it also. So let me open up the simulator. All right, so before coming to the institute, you would have solved lots of problems related to equivalent circuit, finding out the resistance, for example, a circuit given here, and finding out, you're asked to find out what is the equivalent resistance between any two nodes, let's say A and B here. And you would have used a variety of techniques to analyze these circuits. And, maybe you had doubts regarding validity or how a particular technique works. And in that case, when you would like to understand something a little bit better in terms of circuits, what you could do is you could use the simulation to gain a little bit, a better understanding. So just to illustrate, for example, we have a circuit like this, and you would like to find out what is the equivalent resistance. So note that all the resistors are 1. We can easily make all the resistors any other value. The results would scale accordingly. So it's very easy to find the equivalent resistance. All we need to do is, let's say, suppose we take one and then we ground it. And the other end, if I connect a current source. And so current source, let me go to WIF, I source here. And suppose I connect it here, all right? And give it a value of 1 ampere. Right, and let's put the other end ground here. Okay, so if I connect this current source here, 1 ampere, so 1 ampere is flowing here, and obviously it flow through the circuit and will come out here. Whatever is the voltage developed at node A will directly give me whatever is the equivalent resistance of this particular circuit here. So it's very easy to find out. So let's do the analysis, dynamic DC here. Right, so we have dynamic DC here, tells us 1.143, which means that the equivalent resistance between A and B is 1.143, basically ohms here, because that's the voltage at node A, and the current that is going into node A is 1 ampere, so 1.143 ohms here. All right, so it's very easy to find out equivalent resistance between any two nodes. Now, given a circuit like this, you may have one can see that there's a symmetry in this particular circuit, and you may want to understand how symmetry operates. So for example, we could make the circuit a little bit easier to symmetry by splitting the resistor here, R4 for example, into two resistors. So we split it up into 0.5 and 0.5. So we do that. Right, so we've split it up into 0.5 and 0.5 here. And now we can see, if I were to draw a line here, we could see there's a left half of the plane, left half of the circuit, and there's a right half of the circuit, and the two halves are similar. So there's a symmetry, and from symmetry we expect that the voltage at node Vx will be equal to the voltage of node Vy. And another way of seeing it is, for example, same circuit, and if I apply, let's say, 1 volt from here and minus 1 volt from here, right? So 1 volt, we know that if I, the left half and the right half are the same. So if I apply 1 volt, the effect of 1 volt would be to make this voltage positive. The effect of minus 1 would be to make it negative. And because of symmetry, the only possibility is Vx equal to 0. Similarly, this lies on the Vy also lies on the symmetry plane. So Vy will also be equal to 0 here. So we can see that the two nodes are basically, they have the same voltage that is there here, right? So because they have the same voltage, well, we can short this particular node here. So you can see here, we can go back to the previous circuit here. So for example, if we dynamic DC, so let's look at the voltage here. Let's see the voltage here. And because the two node voltages are the same, well, we can short them together, right? So we can see 1.143. Let's short these two nodes together. And note that still, obviously, as we expect, it's 1.143. It will remain the same. So once we short them together, then of course, it's easy to convert the circuit into series and parallel and solve it quickly here. And if you're wondering whether circuits like that have any meaning or they're just puzzles to solve and learn techniques of circuit analysis, let me show you another circuit here. Right, so let's pause for a moment and look at the circuit here. So you would recognize that there is a voltage control current source here, and there are 4 of them. And if you remember from ESC201 theory part there, that a transistor acts like a voltage control current source here. So this is like a MOSFET here. This is another MOSFET here, this is another MOSFET here, and this is another MOSFET here. So this is an N-type MOSFETs here, and these are P-type MOSFETs here. And there's another MOSFET over here. So this is actually the equivalent circuit of a 5 transistor differential amplifier. Differential amplifiers, if you would recall, they are the part of op amps. And this is like the non-inverting terminal, and this is like the inverting terminal here. Right, so we have a circuit like this, and what we have done is we have applied the same voltage to the non-inverting terminal and same voltage to the inverting terminal, which means that the voltage is common to both the inputs, and we call this as the common mode input. And this is where we take the output here, V out here. Right, so we would like to know what is the common mode gain here. When the same voltage is applied to both the inputs here, then we would like to know what is V out by Vs here. And of course, it's very easy to determine using simulation. We can just quickly simulate and show, for example, dynamic DC. If I do, well, it tells us the voltage at the output here, right? The voltage is about -1 microvolt. About 997 nanovolts here, so about -1 microvolt here, and this is 1 millivolt here, so the gain is about -10 to the power -3 here, right? So very small common mode gain, and that's a property of differential amplifiers. These amplifiers amplify only the difference in the voltages applied to V plus and V minus here. Now anything which is common to them, it gets rejected here. Anyway, so we are not going to go into the details of differential amplifier. So the point is we would like to calculate an expression for the voltage gain here. What is V out by V in here? And so we have this complicated circuit that you see here. And if you look at the circuit, one can see that yes, this part and these parts are identical, but this part and this part are not identical, right? In this case, note that this positive terminal here that you see here is shorted here. In this case, is not connected here. So you don't see a symmetry. But a closer analysis of this particular circuit, you may, if you analyze it, you may find that the voltage at this particular node here, and the voltage at this node may be the same for reasons that we will not get into. Suppose you have looked at the circuit carefully and you think that the voltage at these two nodes should be the same. Now you can quickly check whether this is indeed true. So for example, the voltage at this node -997 and the voltage at -97 is the same. Well, we can change it to 2 millivolts because it's a linear circuit, so it won't depend on the exact value. Voltage here still is the same here, right? So this voltage and this voltage are the same, right? So now because this voltage and this voltage are the same and the lower half of the circuit is symmetrical, so now we can use symmetry, the kind of things that we had seen in the previous example here. So we could use symmetry. For example, we could make the circuit more symmetrical by taking this 50 k ohm resistor and splitting it into 2 resistors here. So let's do that. So let's put here. So what we do is we make it 100 k and we'll add another resistor here, right? So we'll add another resistor here, 100K, right, 100K here. Let's put a ground. All right, and let's connect them up. Right, we have not changed the circuit. Circuit is still the same. All that we did was we took the 100K, 50K resistor here, split it into two parts here. So now we can see symmetry in a better way. This part of the circuit, the left half, and this is the right half here, right? They're exactly the same. And as we said, the voltage at this node and this node is the same here. So what we expect is that these two node voltages here obviously are the same. And therefore, we could perhaps break the wire here, right? So let's keep the voltages same. So note that output is minus here, output is there. And so let's break the wire here, this wire here. And still nothing should change because this voltage and this voltage are the same. So there is no current flowing here. So let's break the wire here. Note that there's no change here, still the same. Now what we have done is actually separated the circuit into two halves here. Earlier the two circuits were connected and the analysis was difficult. But now note that the left half of the circuit, because this is ground here, this ground here, so there's a left half of the circuit and there's a right half of the circuit. And so if you analyze the left half of the circuit and you get this particular voltage here, the same voltage would be available at this particular node here. So the point that one is trying to say is that some of the techniques that we use symmetry and various other techniques to determine the equivalent resistance that you may have seen earlier. Some of these techniques are not just puzzles, but they're actually used. Those principles are used to figure out interesting things, important things about interesting circuits. For example, this differential amplifier here. All right, so let's get back to our lab number 2. So in lab number 2, what we're going to do is first part A, we will look at, we'll use circuit simulation to study superposition. In linear circuits, the output voltage, when you have multiple independent inputs, the output voltage can be determined by taking the independent voltages one at a time. So, you could, for example, study superposition using this particular example here. So we get output voltage, which is 500 millivolt. And what you could do is you could make it, let's say 0 here. So you look at the effect impact of V4 only. So you see 333 point so much here. Next, you put this as 0. And you put this as back at 1. And you see the impact here, 166. And if you sum them up, you'll get the value which you expected from this one here, right? When both the inputs are active, right? So you can study superposition and using, so many of the theorems, superposition, Thevenin's, Norton's, many of those things that you've learned, you could, study them through this circuit, or you could pick up any of the circuits that were there in the course, and you could study that as and see how the superposition principle operates. So that's pretty straightforward, right? So what about this here? So consider this one here. So we have made the circuit nonlinear. We've added let's remove this. So we've added a diode here. So how do you add a diode? So let me remove and add it again. So you go here. So you use this one here. Okay, so we use this here, and we click here, and it will give you, there's various kinds of diodes that are there. So we'll use a diode which is commonly available in lab 1N4001, right? So we use this particular one. Okay, so that's how you introduce a diode in your circuit here. Now, the moment you have introduced diode in the circuit is nonlinear. But check it out. How well does superposition work here? When you apply 1 volt and you put this voltage equal to 0, see what the output voltage is. Then when you apply 0 here and you put 2 here, then see what the output voltage is, sum them up, and see whether the output voltage is same when both the inputs are operating. obviously because there is a diode here, a nonlinear element, so you would find that they may not be as good a match as you saw in the previous one. But try the following also. Suppose we make it 10 here and we make it 20 here, right? And see how well superposition works when you have 10 here and 20 here in comparison to when you had 1 and 2 here. And if the error is, obviously in both cases there would be some error, but if the error is far less in this case compared to the previous case, then think about why this is so. Okay, so let's go back to this one here, right? So that's superposition, and you can think about why. I mean, it's sort of obvious, but you can think about why superposition may still be reasonable if the nonlinearity is not too strong. All right, so that's superposition principle that you can study through circuit simulation. Now, what we would want you to do is an interesting problem that we would like you to solve. So here is a circuit, right? So this circuit is given, and and if we simulate this particular circuit, this is what we get here, right? So there are two independent sources, a 10 volt here and a current source of magnitude 1. And if we look at this circuit here, there are these three independent nodes, three nodes here. This one is 10, obviously because of the applied voltage here. This is 11 and this is 7.046. We are calling this node at VG and this is VH here. Now what we want you to do is find out new values of Vx and Ix, right? Right now it is 10 and 1, such that the values of both the nodes VG and VH are 5 volt here. All right, so we would like you to find out the values of Vx and Ix such that both of them are 5 volts here. Now with the simulator there, you may be tempted to start varying Vx, and Ix and do an iterative method of doing it. But what we would like you to do is use simulator to do a few things, but a more systematic method of finding out what is the value of Vx and what is the value of Ix here that you require in order to obtain 5 volt here and 5 volt here. And the reason is that in this case you have two independent variables, and maybe you can try it out, trial and error, to make both of them 5 volt, and you may be able to do it. But suppose I had a circuit in which there were 4 independent sources that are there here, and we had talked about 3 voltages that make this equal to 5, make this equal to 3, and some other node equal to 2, and some other node equal to this, right? With 4 knobs that are there to vary, finding the right set of values for those 4 independent sources would have become more difficult, right? So that's why we want you to think about a more systematic way of finding out the change that I need to do in Vx and the change that I need to do in Ix to force Vg and Vh2, both of them, to be 5 volts here. And maybe you would find superposition theorem helpful here. So think about how you could use superposition that we just talked about to figure this out. Okay, so that's part number C. Next, in part D, we look at Thevenin's theorem. So Thevenin's theorem was taking a particular circuit and transforming it into an equivalent voltage source and a resistor here. And we'll use a particular case where we want to see how we can use Thevenin's theorem to figure out maximum power dissipation occurring in a particular resistor here. So this is the resistor of interest, RL1 here. And so right now, if we these are the voltages that are there here, and these are the currents that are there here, and then this is the power dissipation here. So we have a power dissipation of 5.748 watts here. Now the value of RL is not optimum right now. So what we would like is for you to figure out what is the right value of RL such that the power dissipation in RL will be maximum here. So the only thing that you can change is RL1 here. The rest of the circuit is fixed. Okay. Now you could do that by, for example, finding out what is the equivalent resistance of the rest of the circuit. So we could do a Thevenin's transformation of the rest of the circuit that is there here, and find out, for example, what is the Thevenin's resistance. And then you know the theorem of maximum power transfer, that whatever is the Thevenin's resistance, you should choose the load resistance to be equal to that Thevenin's resistance here, right? So that's where Thevenin's resistance comes into picture here. So Thevenin's resistance would be fairly easy for you to figure out. For example, we would like to find out what is the Thevenin's resistance between these two nodes here, right? Between here and here. And so one way of doing that would be, so right now, let's say it's giving me a voltage of 12.143. So I would like to find out what is the open circuit voltage here between these two nodes. So you could remove RL1 and find out what is open circuit voltage. We could simply go and put a very large resistor. So let me put 15 giga ohms. So that's like an equal open circuit here. So we find that this is the voltage across open circuit voltage is 14 volt here, right? So that's done, 14 volt. Next, let me return it back to 15 ohms here. And we may want to find out what is the short circuit current, right? So let's look at current here. Current is 619, but I want to find short circuit current. So let me put it to 0 here. So that gives me 2.167 here, right? So we had 14 volt VOC and short circuit current is 2.167. So you can find out what is the Thevenin's resistance, which is VOC divided by ISC here. So you can do that, and you can find out what is the optimum value of the Thevenin's resistance here, and then choose accordingly RL1 equal to the Thevenin's resistance, and you can check what is the new power dissipation and all of that is there here. Now suppose, so that's shouldn't take you too much time to do that here. But suppose we make this circuit more interesting. Suppose we remove this and add a diode here, right? So we add a diode here, again 1N4001 we choose, right? So now, okay. So now suppose I have the same task. Let's return it back to 15 here, right? Exactly same circuit, but we introduce a diode here. So we still have to figure out what is the optimum value of RL such that the maximum power is dissipated here. So now I cannot, because of the presence of the diode, I cannot apply Thevenin's theorem because that relies on linearity of the circuit here. So we would like you to think about how you could use the simulator to figure out the optimum value of RL such that maximum power is dissipated when the circuit is nonlinear and Thevenin's theorem is no longer applicable, right? Now in some such cases, what instead of blindly varying the value of RL, one may note that if the diode is forward biased, that the diode can be replaced by 0.6 or 0.7 volt battery here, and then which is an approximation, then the circuit sort of looks like a linear circuit. And then one could determine an approximate value of RL using Thevenin's theorem, and then a little bit of tuning may be required to figure out the exact value of RL here, because the value of RL that you find by assuming it to be 0.7, that's based on an approximation, right? And so that would not be the accurate value of RL, and you may have to tune a little bit. And that tuning would be, if the nonlinearity is not very high, then the value of RL1, the optimum value of RL1 will not be very far from there. And so the tuning will not be that difficult, okay? So you can try that particular approach that is there here. And in the last assignment, part E, we've given a transistor. Right, so this is an amplifier, and you may recognize this as a biasing arrangement here. R1 and R2 and RE are used to bias the transistor, in active mode, and RC is a collector resistance, and we'll not go into the details of the amplifier. So this is right now another circuit for you. And once again, the way you would there's a transistor here, bipolar, so you would click here, bipolar transistor here, right? So you can use various, you could click here and then choose 2 and 2 to 2 here, okay? This is another common transistor that is available in the lab here. So what we would like to figure is the following. Note that this is an amplifier, so you would recall that the operating point in an amplifier is important. Operating point meaning the collector current and the collector emitter voltage here. So let's look at it here. So we can see all the currents here. So this 0.982 milliamperes is the collector current, okay? So that's the collector current. You can see the base currents, all those currents that are there here. And if you would like to see the voltages, then the collector voltage, collector emitter voltage would be 3.5 minus 0.987. So that would be the collector emitter voltage here. So these are the biasing points. The collector current and the collector emitter voltage are important. And all the transistors characteristics depend on the biasing point. So we want the biasing point to be fairly stable. Now what happens is you've designed the circuit and for this particular circuit to operate at, let's say, collector current of 1 milliampere. But now there are problems. All the resistors have tolerances, right? So for example, if you make this particular circuit in the lab, the resistor R1 may not be 20K, and if you use an ordinary resistor, carbon based resistor here, it may have a tolerance of 10%, which means that the value of R1 could be 10% higher or 10% lower. Similarly, value of R2 could be as much as 10% higher or 10% lower. Value of RE could be 10% higher or lower. Similarly, RC. So there are all these variations that are there here. Now note that our interest is that the transistor should be biased at 1 milliampere. But there are these variations that are there here. Not only that, supply voltage that you see 5 volt may also vary by 10%. It could go up by 10%, could fall by 10%. So that's another variation. Apart from that, if we go and look at the transistor here, so if you double click on the transistor, it gives us all the parameters of the transistor here. So there are a lot of parameters of the transistor. Let's focus on beta here. So this is the beta, forward beta here. Now right now the beta is fixed at 200.601. Now the beta of the transistor can also vary. So let's and can vary quite significantly. It may even go as low as 50 and could even go as high as 300. But for the sake of this particular discussion, we'll take that beta can also vary by, let's say, plus minus 10%. So we have all these variations that are there here. R1, R2, RE, RC, VCC, and the beta of the transistor can also vary between plus minus 10%. So what we would like you to do is figure out that if you were to take this particular circuit and make it in the lab, how high do you think, what would be the worst case value of collector current? Worst case in the sense, what would be the, let's say, the maximum value of collector current? And similarly, if you can figure out what is the maximum value of collector current, then by the same approach, you can figure out what is the minimum value of collector current, right? So that this is what we would like you to do that in the lab here, in this particular part here. And so the way to do it is, for example, let's take R1. So the issue is, so R1 we know can go as high as 10% or as low as minus 10%. So should I make it higher or should I make 10% lower? All right, should we make it 10% higher or lower? And so once you figure that out, in terms of its impact on collector current, then accordingly change this to high or low. Similarly, figure out the impact of R2 on the collector current, RE on the collector current, RC on the collector current, and VCC on the collector current here. And for all of them, find out the impact and accordingly increase or decrease them and find out what is the maximum value that you can possibly get in the lab if you were to make a circuit like this. Now the simulator is more powerful. Simulator would allow you to vary R1, R2, RC, RE, VCC, all of them simultaneously, and you can get a plot of, it can figure out what is the worst case maximum or minimum values of IC. But in this case, we would like you to, by yourself determine what is the impact of R1 on collector current and accordingly make it higher or lower here. Right, so, and since we are talking about, even though the circuit is nonlinear, but we are talking about small changes, so we could consider the impact on collector current to be linearly related to all these changes that are there here. So as you try to find out the, so you could just sum them up. All right, so so these are the things that we need to do. Superposition. The first part is very simple. The second part, look at superposition with a diode being there for two different values of voltage, 1 and 2 here, and 10 and 20 here. The third part is find a systematic method of determining the change required in Vx and Ix to force these values to 5 volt here. Then the fourth part is using Thevenin's theorem to figure out the optimum value of RL1, first without the diode, and then with the diode figure out what is the correct right value of RL here. And in the end, find out what is the maximum value of collector current that can occur due to variations in the components that you see there. All right, so let's stop here.